Hi, everybody.
Hello.
Hello.
How's it going? Let's wait a couple minutes to see if more people log on, or a minute or two. All right. Okay, we'll see a couple more people coming in. All right. Hope everyone had a good weekend. Any questions at the beginning of class? Okay. If not, let's get started. Okay. All right. So the next goal. The next goal is to prove the following theorem. Actually, just give me 1 second. Let me just define some notation. Some notation that I'll use a bit, but then at some point in class we'll kind of forget about. So I'll use script R of t to be equal to this is defined to be the set of all f from the circle for the complex numbers such that, so these are just the Riemann integrable functions. F is Riemann integrable. So it's a Riemann integrable function on the interval 0 to 2 pi, and we know that the continuous function, for example, the continuous functions are a subset of the Riemann integral functions on the torus circle. Okay, with this notation, we're going to prove the following theorem. So I'll call this the L2 convergence of Fourier series and Parseval's theorem. So there are two parts. So one, the setting is suppose f is a Riemann integral function on the circle. Then part one, so we have L2 convergence. So 1 over 2 pi, the integral from minus pi to pi of f of theta minus Sn f of theta squared d theta tends to 0 as n goes to infinity. So we have convergence of Fourier series, but in this average sense. So after integration, and two is that this is called Parseval's theorem. This is a deep theorem. But both of these, this whole thing is a deep theorem. And as we'll see coming up, this is somehow the proper setting in which to interpret Fourier series, or one of the most useful settings in which to interpret it. So Parseval's theorem says that well, not only do I have L2 convergence of Fourier series, but the following identity holds: integral from minus pi to pi f of theta squared. If I take my function, square it, and integrate, this is equal to the following sum of the squares of the Fourier coefficients. Okay, so this is a remarkable fact, and as we'll see before, this basically is going to amount to understanding a bit of the structure of what I'll call L2 and little L2, and vector space theory in particular, what are called Hilbert spaces. Okay, so let me give you some more notation. So or let me set the stage maybe for this theorem. Does anyone have any questions about the statement? In particular, this means for any continuous function, you have we have convergence of Fourier series in this sense, in this average sense.
I guess I have a question, more of a meta question.
Yeah.
We've been doing a lot of convergence and different means of convergence and so on. Does anything that we've covered in the past apply to these Riemann integral functions? But like, is everything we said previously applicable not just to the continuous, but also to the Riemann integrable functions? Or is that not necessarily true?
Okay. Yeah, not necessarily. So some of the things that we said in the past, in particular, if we're asking about the convergence properties of, say this difference at a particular point, it doesn't really make sense, that question, for just a Riemann integrable function, right? Because two different Riemann integrable functions, or two functions, can just be different at a point, but have the same, be kind of the same from the view of their Riemann integralness. We'll flesh this out a bit more today, but I think this in particular will help us clarify that your question a bit more. So some of the things that we would prove a result, and the way to strengthen it would be, we prove a result for continuous functions in the past few weeks. And often the way to strengthen it wouldn't be, oh, it holds for Riemann integral functions. Rather, the strengthening would be something like, oh, this type of convergence result holds at points of continuity of a Riemann integral function. So that would be the type of strengthening that was often available in the past few weeks. But like, this is some of the questions just straight didn't make sense. But that's a good point. So we'll start seeing that. We'll understand this more as we go, I think today a bunch in the next few classes, some of these distinctions. But yeah, and just to further elaborate on your question a little bit, you're right about what we've been doing and what we'll continue to do for a couple more classes. We've really attacked the same question over the first 3 weeks or so, by a bunch of different, we've tried to answer it in a bunch of different ways. And it's sort of hard to keep track of like how these all fit together and why in particular we're asking in all these different ways. But maybe just like kind of just bear with me and a bit. And we'll try to put it all together. But I guess one of the things that is that one thing just to note is that there are just a lot of different ways of attacking this question, and some of them you can kind of grade them on how useful they are, say, in deducing other things that are of interest, right? Okay, and I claim this way of attacking it is going to be particularly fruitful. So we're going to ask about convergence of Fourier series, but in yet a different way. Convergence in terms of in this integrated sense, L2 what I call L2 integrated sense. All right, so let me kind of get to the bottom what I mean by this L2. Okay, so we're going to take a step back before we answer the question. So the proof. we'll use some abstract theory of inner product spaces. Which is an inner product space is a vector space with an inner product. And let me tell you what those are. So and so let me just say one more word. So what I mean by this abstract theory? So in particular, I mean what is the abstract theory? The notion of orthogonality. Okay, so some preliminaries on vector spaces. So vector spaces over R or C. Okay, the real numbers are a vector space over R or C. We say that V over V is a space of vectors. V is a vector space over RC. If for every x, y, and v, if you have two elements in V, and lambda, say a complex number, a real number, these imply that that x plus y is in V, and lambda times x is in V. So the space is closed under addition and multiplication by scalars. And these two operations are by the usual laws of arithmetic. Okay, so that's the vector space. And we're not going to just concern ourselves with vector spaces, we're also going to endow them with some more structure. So we'll say an inner product space is a vector space endowed with an inner product. A vector space V endowed with an inner product. I'll use some angle brackets for inner product. Where the inner product, maybe I'll write some words for an inner product. It's a mapping. So this angle bracket thing with these dots are supposed to be placeholders for the input into this function, in this mapping, is an inner product from V cross V, so from two copies of V, to R or to C. So for a vector space over C, then the inner product will be will be allowed to take complex values. If for a vector space over R, we're going to just allow our inner products to take real values. And we'll write this as X and Y. So a pair X and Y gets sent to X inner product with Y. So this is what the mapping looks like. So that let's do the case of a real inner product first. So just let me just erase C for here now. So a real inner product space is so that this is symmetric. i.e. inner product of X and Y is equal to inner product with Y with X. linear in both variables, and positive definite. So the inner product of x with itself is bigger than or equal to 0 for every x in V. Mapping with these three properties is a real inner product over a real vector space. And once we have an inner product, then we also can endow V with a norm. So an inner product gives a norm on V. The norm of x is defined to be the square root of x inner product with itself. So inner product give rise. So once you have an inner product, then you have a notion of the length of a vector on your inner product space. And then one other tidbit. So if the inner product, if the norm of a vector is equal to 0, implies that x is the 0 vector, then we say this inner product is strictly positive definite. Okay, so this is just some language. So an example of a real inner product space, RD, where the inner product of two vectors in RD is just given by their dot product. So familiar dot product from calculus. So if x is equal to x1 xd, y is equal to y1 to yd, then x1 y1 plus xd yd. So that's a familiar example of a inner product space. It's just the Euclidean space of dimension d. The definition of we require or a slightly different definition in the case that we have a complex vector space. So in the case of, so if V is a vector space over C, is a Hermitian inner product, we'll consider this case, which contains the other cases, like is a Hermitian inner product if if you have the following. So it's a mapping as before, V cross V, this time to the complex numbers, such that xy is to yx, but the complex conjugate of this. So if it's not symmetric, but it's symmetric for conjugation. So if you have if this is true, linearity holds in the first variable. So meaning if I have alpha x plus beta y paired with z, then this is equal to alpha beta yz, where alpha, beta are in C, and conjugate linear in the second variable. These are properties so that it plays nicely with complex complex numbers. It's alpha bar xy plus beta bar XZ. Okay. So it's an inner product, but we also give rise to, it also gives rise to a norm. So same as before, the rest is the same. And an example here, the canonical example here, is the vector spaces CD, so so d-dimensional, so d copies of the complex plane, where z paired with w is equal to z1 w1 bar plus all the way out to zd wd bar. This is all z1 through zd ordered pairs like this, where zj is in our complex numbers. So d-dimensional complex space. And then the length of a vector, in this case, z, is equal to, again, this is just, once you have an inner product, it gives rise to a length, which is equal to I'm not sure what happened there. One second. Okay. So is everybody with me so far? I haven't done much. I've just made some definitions. Notion of inner product and at least in the plates in the this first example should be familiar. So Euclidean space with real Euclidean space with the dot product as the inner product. This is the complex dot product. Okay. So a couple more, some more structure. So the notion of orthogonality. Orthogonality. Say we have an inner product space V. We say x is perpendicular to y if, or x is orthogonal to y if their inner product is 0. And the concept of orthogonality, you should, so in say R2, draw a picture of what this means. If you have two vectors, then the picture is looks like this. Two vectors that form a right angle with each other. So they or this is where we get the name orthogonality or perpendicularity, or the perpendicular signal sign. Okay, so some consequences. So some facts about inner product spaces. Now we have this notion of orthogonality. So if x is perpendicular to y, then the Pythagorean theorem holds. Or the Pythagorean identity holds. Which is that the length of x plus y squared, the norm of x plus y squared, is equal to x squared plus y squared. So if you have two perpendicular vectors, then the Pythagorean holds. The Pythagorean theorem holds, right? Which is you can see by completing the triangle in this picture here in R2. But this holds in general. This is, we've made more abstract this the Pythagorean theorem. Two, the Cauchy-Schwarz inequality holds. Wait, which Schwarz is this? Cauchy-Schwarz, this guy. So the absolute value or the length of the inner product of between x and y is always less than or equal to the norm of x times the norm of y. And you have equality if and only if x equals y in the setting. This suffices to state it like this. And then point 3 is a triangle inequality. So we have this norm coming from the inner product, and the triangle inequality holds. So x plus y. The length of x plus y, the norm of x plus y is less than or equal to length of x plus length of y. That's the norm of y. And what this means is that we also this gives us a metric. So the inner product space becomes a metric space, and the distance between two vectors x and y, we just take to be the square root of, or rather, just write it like this. It's x minus y. Okay. So you get this is a metric. This is a metric. Okay. Okay, so more examples. The ones that'll become any questions at this point, maybe? I give a couple more examples, ones that'll be most relevant to our discussion. So examples. So we can pass to the infinite dimensional setting. We just the previous two examples I gave were finite dimensional vector spaces, but this is an analysis class, so we won't be limiting ourselves to those, unfortunately. Pass the infinite dimensional setting. And the first example is called L2 of Z, little L2 of D, so a lowercase L2. This is the set of all two-sided sequences of complex numbers. So it's a set of all sequences. And I'm going to tell you what the inner product is. Such that set of all two-sided sequences should specify.
I have a quick question for you.
Yes.
So what do you mean by, I guess, two-sided sequence?
Let me write those down.
Oh, okay, cool. I didn't know if you were going to get to that or not. Thank you.
Yes. Maybe let me. This is a weird. I.e. A sequence AN is in L2Z. This is awkward. AN, hold on, equals the sequence of numbers, but I let n be indexed over z, as we've been doing in class, rather than just the positive integers. So this is infinite sequence, a minus n, a minus 1, a0, a1, an, etc. So infinite sequences, two-sided, meaning that they're indexed by z, rather than just natural numbers. So two-sided meaning like negative indices, such that they're square summable. That's the closed bracket finally down there. So this is so the point is we want to think of sequences as elements of a vector space. So this is the norm. Actually, let me write this. The norm of the sequence in the L2Z is given by just square summing the sequence. Think of sequences of a vector space. Okay, so what I said is an inner product space. The inner product of two sequences. If I have one sequence and I inner product it with another sequence, this is defined. I'll write this as L2Z. The L2Z inner product is defined to be, I just take the sequence of AN times BN bar. And then the norm, I'll write this again, of a sequence. The little L2 norm squared, this is a square of it, is given by the sum over N and Z of the take the modulus of each complex number, the absolute value, I square it, and then I sum. Okay. So this is infinite. I said this is infinite dimensional because you can kind of just see by examination that there's no finite collection of sequences that span this vector space. So you can think about that, but this is not a finite dimensional vector space. Remember the dimension is like for case of vector space is a minimal, the number of vectors in a minimal spanning set. And the second example, second example will be relevant to today's discussion, is say the Riemann integrable functions. So I'll call this L2 of the Riemann integrable functions. Maybe I'm going to get rid of not use this L. I'm going to not quite use that L2 big L2 yet. So the vector space is R of T. So the Riemann integrable functions with norm with inner product I'll call this the L2 inner product is I do 1 over 2 pi minus pi to pi f of theta times g of theta bar d theta. So this is a Hermitian inner product. And just to think of this as a vector space, so we can add two functions together. So f plus g is the function defined pointwise by pointwise adding the elements. And then lambda times f is the function of theta is lambda times f of theta. So that's how I view this as a vector space. I just multiply a function by a complex number, I get another function. I can add two functions pointwise together, get another function. And then in this setting, the L2 norm of f squared is equal to 1 over 2 pi, integral from minus pi to pi of, so if I take f and I multiply by its complex conjugate, I get the absolute value squared of f d theta. So this is the L2 norm of a function f. Okay, so these are the two examples we're going to consider, and let me reframe the theorem that we stated at the very beginning of class. Now, with so this Parseval's theorem and its L2 convergence. With this, I've understood the structure on the space of sequences and the structure on the Riemann integral functions of the vector space over the complex numbers with a Hermitian inner product. So the theorem can be rephrased as theorem. So this is the same as before. L2 convergence. So if f is a Riemann integral function on t, then 1, the L2 convergence result is just I have converged in this sense. Right, this is the L2 norm of a function. And so the first part of the theorem was precisely this, was this statement. And 2, the second part, this is L2 convergence. 2 is called Parseval identity. Is that the L2 norm of f, given a Riemann integral function, the L2 norm of f is equal to the little L2 norm. So associated to a Riemann integral function f, we have its sequence of Fourier coefficients, and then that's a sequence in. It turns out that is a sequence in little L2z. So this is little L2. Let's see. So you have a identity here. Maybe I'll put squares here. Well, just like this. Okay, so the neat structure is that we have a mapping. So we have a mapping from if we take a function f from the Riemann integral functions, we associate to it a sequence. It's sequence of Fourier coefficients, and this is a mapping. It turns out, if we start off with a Riemann integral function, we end up. Parseval's identity tells us that we end up in L2z. So we have a mapping. So we have a mapping from Riemann integral functions to L2z, and it preserves norm. So we're going to flesh this out more. We're going to ask more about this mapping in a bit. What we'll see is that, in fact, the entire vector space structure is preserved. So including we have this identity of norms. And okay, so one more bit. This is going to lead us right into our question about measure theory, or this is going to lead us right into the need for measure theory in the Lebesgue integral. Is just one side comment. So remark. Let's see. maybe I'll not this, we'll make this remark. Yeah, let me discuss this now, just a bit. We're going to come back and discuss this again later. But okay, so we have this mapping here, right? If we believe the theorem is true for a second, we the result is this mapping. We have parcel identity, which is it's a map. We say that this mapping preserves, in fact, preserves this norm, and so you can ask how much of the vector space of the vector space structure is passed on from this mapping. You can also ask, is it one to one? Is it onto? Is it a bijection? Well, let me add one more definition. So we say an inner product space V with the inner product is called a Hilbert space if we have two additional properties of the inner product. One, this is strictly positive definite. Not just positive definite, but strictly positive definite. So so i.e. this is true. If the vector has zero length, then it's a zero vector. But two, V, I showed you that once we have an inner product, then we can endow the space with a metric. And then so inner product space is also a metric space. And then you can ask, in the sense of your real analysis class, whether this metric space is complete or not as a metric space. So two, the second inner product space becomes a Hilbert space if V is complete with respect to the norm, which means i.e. every Cauchy sequence converges. So completion, if you remember from your real analysis classes, once you have a metric space, you can discuss Cauchy sequences and then ask if then you make a definition. So if every Cauchy sequence is convergent, then you say the space is complete. If every Cauchy sequence converges. Okay. All right. So, and then we'll see in homework. I'm pretty sure I assigned this problem that L2Z is complete. Is a Hilbert space. So any Cauchy sequence of sequences is convergent. And then I want to know about this mapping that I defined here on this page, where I associate to each f its Fourier coefficients. It turns out that that the mapping is not onto. Okay, so let's discuss real quick this vector space with the L2 inner product. So unfortunately, this is not quite a Hilbert space. A Hilbert space. Well, in fact, both of these two additional requirements fail for Riemann integral functions. On the one hand, right, you can have a function which Riemann integrates to zero, not be the zero function. Like the function could be zero everywhere except at one point. That function has zero integral, but it's not the zero function. All right, so that's actually kind of a mild problem, and we'll see later that this is kind of that's not catastrophic for the space of Riemann integrable functions. You could just say, well, I'm going to just call any Riemann integrable function that's equal to zero function that integrates to zero, that has L2 norm equal to zero, the zero function, and that kind of solves the first bullet point of trying to be wanting to be a Hilbert space. The second bullet point, though, truly fails, and this is the sense. So the next part of the class in a week or two, we're going to start trying to complete the space of Riemann integrable functions with the L2 inner product to a Hilbert space. So we're going to try and find a bigger space that contains the Riemann integrable functions that is now complete with respect to this metric. We're trying to fill in, right, just like with we had the rational numbers in analysis class, and this failed to be a complete metric space, the natural metric on the rational numbers, and we completed it to the real numbers by kind of adding in all the limits of Cauchy sequences, and we're going to do the same thing with Riemann integrable functions to enlarge them to the class of what are called Lebesgue integrable functions, and this is going to be the complete vector space that we're looking for. So once we do that, then this mapping, it will not just be a nice mapping with this identity being true. It'll actually be a isomorphism of Hilbert spaces. So it's one-to-one onto and it's called a unitary isomorphism. In fact, the norm is preserved under this mapping. So this our goal in developing measure theory and the Lebesgue integral will be to make this mapping here what's called a unitary isomorphism. So we're going to try and find the space, find the right domain for this mapping. So that's a preview to come, and this question motivated the development of the Lebesgue integral. For now, though, I can show you by means of an example, or you'll flesh out in your homework by means of an example why this is not complete. Well, I can give you in fact, your book gives you a nice example of functions, a sequence of functions which fail, which are Cauchy but don't converge. So example, completeness fails. For example, if I take f of theta to be equal to the function 0, if theta equals 0, and log of, say, 2 pi over theta, if 0 is less than theta 2 pi, then this is not, then f is not Riemann integrable. So you can check this integral doesn't make sense. This is a bad function, has a bad singularity at 0. But if I take fn of theta, so I'm going to find a sequence of functions defined to be 0 on for theta for 1 over n if I make the function identically equal to 0 up to 1 over n, and if I make it equal to f of theta, if 1 over n, maybe I strict inequality at this endpoint, then this is an exercise. Fn of theta is Cauchy in L2 of the Riemann integral functions. But f is not Riemann integrable. So you have a Cauchy sequence. You can check that this sequence here is perfectly Riemann integrable because I've just moved away from the problem at the origin. And it's Cauchy. So if I measure the distance, measure the L2 distance between Fn and Fm, then that distance in L2 is small for as long as n and m are both large. Can be made small for both n and m are both large, as small as we like. So it's a Cauchy sequence, but it would have this sequence, if it converges to anything, would have to converge to this function, right? It just clearly that's the only choice is for the fn's to converge to f, but f is not Riemann integrable. Okay.
Quick question
Okay.
about that.
Yeah.
So I guess it's pretty clear to me that if the fn's converge at all, then if they converge pointwise, then they converge to f. But
Yeah.
I thought we were talking about if the fn's converge in L2 to f, which is a little different.
Yeah, it is different, but it's kind of like it looks like if so I want you to flesh this out in your homework a bit, but that's the only reasonable answer for a function that converges to, right? Right. If we think of L2 convergence as if you think about if L2 converges is a reasonable notion of convergence, then this is sort of the only candidate function.
Sure.
Right. I get so that's the extent to which I'll get into the detail now.
Okay.
But you're right. It's what's clear is that we have pointwise convergence, right? But I claim that this is somehow that's a somewhat stronger notion that converges in an average sense.
I have a question. So looking ahead, would that imply that this f of theta, is that Lebesgue integrable? Is that the conclusion that we're going to get eventually? It's Lebesgue.
We'll try to get to understanding. Yeah. So we'll try to we'll want to be able to integrate such functions. Yeah. Or understand their integrals. Okay. Okay. All right. So let's get back to proving this theorem. So and you'll see now with once we're going to exploit the concept of orthogonality, and in particular just the Pythagorean theorem, and this is going to kind of fall in our laps for us. Okay, so proof of the theorem. Okay, so the first observation is that the functions, I'll call them En of theta, defined to be e to the I in theta, are an orthonormal family. So if I take the inner product of two of them, we did this computation already. This is equal to 1 over 2 pi. This crucial computation. E to the I n theta, e to the I m theta bar d theta, which is just equal to 1 over 2 pi minus pi to pi. E to the I n minus m theta theta. This is equal to 1 equals m and 0 otherwise. Right, so this is an orthonormal family of functions, and as we'll see, this is in some sense this is like a basis. Moreover, the Fourier coefficients, what are those? So f hat n of a function, this is 1 over 2 pi, integral from minus pi to pi, f of theta times e to the minus I in theta, d theta. This is nothing other than f paired with en, the inner product of f with the function en, right? It's f with the complex, multiplied by the complex conjugate of e to the I in theta, and then integrated. So this is the the Fourier coefficients are nothing more than taking inner product of f with en, i.e. projecting f. If you go back to your calculus days, this is the projection of f, the coefficient of the projection of f onto en, right? And so what are the partial sums? So i.e. SNF is just the sum of all n less or equal to n. Sorry, this should be capital N. Of the Fourier coefficients, which are f, the coefficient of the projection, times en, right? So this is just taking the span, the n plane, the span of these functions en in L2, and then taking the projection of f onto them, onto this plane. Right, so this is it turns out, so the partial sums are a natural geometric thing, right? There's geometry in a Hilbert space, or in a vector space. Okay, well, now that I've written it like this, did I say proof at the beginning? Yeah, proof, okay. Now that I've written the partial sums like this, note that this implies that if I consider this difference, this I claim, which is equal to f minus this is perpendicular to em for every m less than or equal to n. Right? Why? How do I see this? So why? How do I see this? I just can compute. So I take f. So if m is one of the first in integers, and I pair f with em, this is just equal to. Sorry, I want to consider this difference. Minus this whole thing paired with this whole sum paired with em. Then here everything collapses, right? These are all orthogonal to each other. So I only pick up a 1 when n is equal to m, and then I just have I'm just left with that coefficient there, which is f paired with em. So this is equal to which is 0. So this whole object is perpendicular to em. Well, therefore, this is perpendicular to every trig polynomial built out of the first n Fourier coefficient in integers. So therefore, f minus SNF is perpendicular to the sum, any sum of the following form, bn times en, for any complex numbers. Okay, so now let me apply the Pythagorean theorem. So I apply a Pythagorean theorem. to F equals F minus SNF plus SNF, which means, so then I apply the Pythagorean theorem. So this is, so L2 squared is equal to F minus SNF L2 squared plus, right, because this in particular is a trig SNF of the form. So these two things are perpendicular to each other. So I just apply the Pythagorean theorem. Sum from n f hat n e to the n times en L2 squared. Okay, so now I have a nice representation of the L2 norm of f in terms of these two quantities on the right hand side, and I note that so observe that this last quantity well, all the cross terms vanish, right? Because if I just expand this out, this is just equal to the sum of f hat n squared, right? Because all cross terms vanish. Are people with me? Am I going a little bit too fast?
Can you explain that cross terms thing a little bit slower?
Yeah. So what's happening in this sum? So what does this sum consist of? It's right. This is I need to take 2 copies of this. En, the sum over all these, and then I pair it with, sorry, I drop it. I often use that notation. Personal life. Maybe I'll use m's for the index over here. I'm not sure why I'm including. So that this on the left hand side is equal to this pairing, and then what is made up of terms f hat n times f hat m bar times the inner product of en with em. So there's a bunch of, this is right, you have to expand, this is a inner product of 2 sums of vectors, and I need to expand them. The cross terms are mean when n is not equal to m in these matchups. And all of those are then 0, right? If equals 0.
Because it's an orthonormal basis, right? So
exactly.
Yeah.
So this is the EMs are orthonormal or an orthonormal family.
Perfect.
So
Thank you.
all the cross terms vanish, and I'm just left with this sum. So if I go back to my identity here, if I plug in this sum for this expression here, what I've just proved, so therefore, maybe I'll. So I prove this identity. Maybe I'll call this one star. And if I go back up to the main theorem, I note that once I prove the L2 convergence, once I prove that this goes to 0, by letting n go to infinity, then I recover Parsifal's theorem. Then at the remark 2 follows from 1 plus star by letting n go to infinity and star implies that so by letting n go to infinity in the star inequality, I get Parseval identity. So this is Parseval. Okay, so this equality star is very nice. It gives me Parseval's identity. Once I've proved the L2 convergence of Fourier series. So I'm kind of left to prove one, the L2 convergence, and okay, via similar argument to getting star, I can prove what's called the best approximation lemma. So lemma. So I'm just going to pause the proof and prove a lemma, a useful lemma. Which tells us that the Fourier partial sums are the best approximation for a function. The partial Fourier sums are the best approximation for a function in L2. You can't do better. If I'm just looking amongst trig polynomials. So if f is a Riemann integral function, then f minus SNF in L2 squared is less than or equal to f minus the sum Cn En for every in C, in the complex numbers. And moreover, equality if and only if Cn's are equal to the f hats n's. So if I think of, the trigonometric polynomial obtained by taking the partial Fourier sum is the closest I can get to. It's the best approximation for f amongst any other trig polynomial of the same degree. All right. So in particular, it's better than the Feyer kernels, for example.
That's pretty surprising, right? I think like if you add, because like the Fourier sums, like for example, like if you take the first order polynomial, right? The first order trig polynomial, like the S1, but then you expand it, then the coefficient on the e to the plus 1 theta still stays the same, right? Because you're only adding terms and you're not changing the old ones as you increase n.
Sorry, I didn't quite follow the example.
Like if you move from like S1f, which might be like, I don't know, like 1 plus e to the like I theta or something.
Yeah.
But then if you expand it to the second order, it's still e to the plus 1 I theta, and then you get a, let's say, 2 e to the 2 I theta or something, right? But the coefficient on the first I theta still remains the same.
Yeah.
And so you're saying that that is still the best like approximation.
So in
kind of
so of degree n.
Of degree n, right?
Sorry, that this is so right. So on each side, sorry, I erased something by mistake. But on each side of this equality, I have this n is fixed.
Right. That's kind of surprising because, like, I guess the example I'm thinking of is like when you do a regression, and like when you add a new variable to a regression, then the regression by default like picks the best approximation, and the coefficients change whenever you add a new variable or you add a new basis vector, kind of.
If I'm only looking at Fourier, yeah. If so, this is cool, right? It tells us that we're doing something deep, kind of, right? This is the best L2 approximation if I'm looking amongst trig polynomials of degree n. You can't beat it, like you say. No matter it turns out that the best way to, if I want to up the degree of approximations or up the degree of the polynomial, then the only thing I should do is just add the next Fourier coefficient as the coefficient of the polynomial of one higher degree. Yeah. So this is a big deal, right? And this is also signaling to us that we're kind of, this is sort of the natural setting for Fourier series is L2. This L2 inner product space is very natural. In fact, we're doing this this is somehow optimal here, if we're thinking about approximating f by trig polynomials. Okay, so what's the picture? And you were telling me you have the right picture in your head by the question. Or maybe let me prove this real quick, and then let me draw a picture. So the proof is just apply the Pythagorean theorem to f minus Cn En, where the Cn's are arbitrary complex numbers. I take this to be a trig polynomial of degree capital N, and I can rewrite this. So maybe so f minus is equal to f minus Sn, f plus the sum from n less than or equal to capital N of f hat n minus Cn En. Right, so I just rewrote this difference by adding and subtracting S and F, and then I apply Pythagorean decomposition. So 2 is equal to plus this, which is just by the same logic as before. This is just squared. Right, so that means that this plus this positive thing is equal to this. Right, so this has to be less than or equal to this, and I see I have equality if and only if the f hat n's are equal to the Cn's for every n. So this identity proves the theorem, proves this lemma. And the interpretation is that if I think of the span of En as a plane, and I think of the function f as a vector in the Hilbert space, in this vector space, then the this S and F lies in the span of these En. It's a vector in the span, and this is orthogonal projection onto this span. Okay. Yeah.
So have any of the results so far depended on anything other than that the trig polynomials form this orthonormal?
Yeah, that's it. That's all we've used so far. Yep. We've just used this fact that these is an orthonormal family. And you're onto something. Like you might think, what if I take a different orthonormal family? And you still have these same results still hold, like the best projection, the best approximation theorem, etc. Okay, so let's complete the proof of the L2 convergence to complete the proof of the theorem, and this is a little cheap. So if, say, f is continuous, if f is a continuous function, we already proved there exists a trig polynomial that's arbitrarily close pointwise to f, right? The trig polynomials were dense. That for every epsilon bigger than 0, there exists an end such that sigma in f minus f in absolute value in L, say in L infinity is less than epsilon. Right, you can approximate f by a trig polynomial, in particular by taking the ones obtained by, say, via the Cesaro means of f. But then now just apply the best approximation lemma. But then, which is equal to squared, which is less than or equal to just the soup, just as since this is only an interval of length 2 pi, this is less than or equal to sigma n squared, which is less than epsilon. So we can always, so you give me epsilon, I find that a capital N such that this thing is less than epsilon. This is by best approximation lemma. And we're done for continuous functions. Okay, you might object, well, we said...
Sorry, can I
yes,
interrupt? I mean, should have epsilon square, but I guess doesn't really matter.
Sure, yep, even smaller. Yeah, and okay, so this is just for continuous functions. And then for if f is Riemann integrable, this doesn't work anymore. But in book, you can find, can see how to approximate first by continuous functions. So first, if you have a Riemann integrable function, find a condition that's close to it in L2. The book shows you a way to do this. And then after you approximate by continuous function, just apply the previous argument to that continuous function. So first approximate continuous function by Riemann integrable function by continuous function, then approximate the, then apply this previous result here. So just, it's this approximation theory that I haven't covered yet, because we're going to do it a little bit, we're going to do it more carefully with, in a few weeks. And then apply this previous argument in the triangle inequality, and you're done. So so that's the theorem. Yeah. So that's the theorem. Any questions about the proof? Okay. Now we can apply. Now that once we know part one, right, we can apply it to obtain Parseval's identity, which is part two. Here's the theorem. Here's the statement of the theorem.
I have a question that's somewhat related.
Yeah.
Is there like an analog to the best approximation lemma in like the Taylor series, for example? Would do the sequence?
Not really. Well, okay. Yeah, not really. It's what we're really relying on here is the fact that we're expanding. We're looking at polynomials where, but where what we're doing is we're expanding in an orthonormal basis, and in the Taylor series, you expand in like powers of x or something like that, right? Around, if you want to find the Taylor series of a function around 0, then you expand in powers of x. And those aren't you can consider, say, the L2, same like L2 type inner product, but those aren't orthogonal to each other anymore. So this perspective breaks down, where you, like, as was pointed out a second ago, what we're really doing here is we're really just leaning hard on this vector space structure that where do they go? These ENs, these guys are an orthonormal family of vectors. It's kind of a basis. So the best approximation lemma holds once you've picked an orthonormal basis and want to try and expand in polynomials in that basis. Or expand in that basis. I shouldn't say polynomial anymore. Just expand in that basis. Sorry, yes?
Sorry, I was just going to ask, but isn't there a set of orthonormal polynomials that are not the ones you use straight in the Taylor expansion? But
yeah. So yes, right. You just have to choose to, you want to try and expand in a different. I mean, this best approximation lemma that we proved is a Hilbert space lemma, and it's about like orthonormal families, and it holds in that generality. But for Taylor series in particular, a Taylor series is specific about expanding in just like x.
Just powers of x.
Powers of x, yeah.
Okay.
Yeah. Yeah, so just slight distinction in what we mean by expanding, and it so happens that these trig polynomials are polynomials somehow, and yeah, and so they're the two sort of expansions sort of collide, where the Taylor series you're expanding in a polynomial too, but it's in powers of x. Here, it's a trig polynomial, but it's also the elements. It's also you're just projecting onto the span of an orthonormal set of vectors. So it's like the linear algebra and this expansion in polynomials kind of collides in one, or is merged in one. But I hope this structure here kind of tells us that this is somehow a natural setting in which I should be considering Fourier series. This looks nice. Like, once we start doing linear algebra, then you used to say, okay, maybe we're like barking up the right tree. No, so this looks pretty. So what will be prettier is if this mapping, where we associate to a function its Fourier coefficients, if this mapping is like a 1-to-1, is an isometry. So is a isomorphism, and we proved if we can find the right domain for the functions, then I have what's called a unitary isomorphism. It preserves the norm, and it's a 1-to-1 onto bijection, preserving all the inner product structure and everything. So we're gonna that'll be our motivation for measure theory, for developing measure theory, and it was the motivation for developing measure theory. In fact, one of the main. There are a couple other questions. We'll talk about each of these questions, but there are a bunch of things converging at the turn of the 20th century that were better. Finding the right domain for this mapping in particular. Okay. So we'll start next time. We're not going to quite launch right into measure theory next time. We're going to decide to fight even harder on the convergence question for a bit, and then before we get there.
Can I say something about the question we've just asked about the linear regression thing?
Yeah.
Because he said that the coefficient change when I add more variables, but then it's just because the matrix we have used is not orthogonal itself. So if we try to use an orthogonal design matrix, then we will definitely have the column of the matrix will actually be orthonormal, and then we can sort of use the best approximation theorem here.
Yes.
Should we?
Yeah. Yes. yes, yes to all of that. I think, if I understood correctly. Yes. Thanks for the remark. Okay, guys, I have to go. I have to go to a seminar now and jump onto yet another Zoom call. I'll see you guys on Thursday.
Thank you.
Thank you.
Bye, guys.